set of ideas on hypothesis testing. So we have a basic problem within the decision theoretic framework. But the question that we ask is simpler rather than trying to specify the entire parameter. We just want to decide whether it lies in this section of the parameter space or this other section. So omega naught and omega 1 are two pieces of the parameter space. So they form a partition. So we have omega naught and omega 1. And then you're looking for a test. And the idea is that we want to sort of find a test which maximizes this power function, if you recall, is the probability rejection of the null or the acceptance of the alternative under the true model parameter theta. So when the true model is p theta, what is the chance that we accept the hypothesis? And this can be written as the expectation of the test, whether it's deterministic or randomized. So this expression always holds. And so the expectation of a test will give you the power function, and then the power of the test is the minimum that this power function attains on omega 1, and the significance level or the level of the test is the maximum that it achieves over the norm. So we want this maximum to be as small as possible, this minimum to be as high as possible. So in the Neyman-Pearson framework, we maximize. So this is called, the first one is called alpha or type 1 error sometimes. The second one minus the second one is the type 2 error. But usually you want the type 1 error in power or the significance level on power. So we want to maximize the power subject to an upper bound on the significance level. And in the simplest case, not surprisingly called the simple hypothesis testing problem, we have a node which is a singleton and an alternative which is also a singleton. And the idea here is that the Neyman-Pearson criterion that we discussed just reduces to this optimization problem. So both the power and the significance level, those optimization, the sup and inf just collapse to one point. So this is the power of the test. So what is the acceptance probability under theta 1? So we want this to be big, so we want to maximize this. And then what is the acceptance probability under theta naught? We want this to be small. We don't want to accept under the null, right? So we set an upper bound on this alpha. The subject to this we want to maximize. And the solution of this problem is given by the Neyman-Pearson lemma, which states that first, the solution of this we can call the most powerful test for a given significance level alpha, for the given significance level most alpha. So the optimal test is called most powerful test for obvious reasons. And so Neyman-Pearson, there's this lemma called the Neyman-Pearson lemma, which specifies what exactly is the most powerful test. So the most power is achieved by the likelihood ratio test of this form. So you form the likelihood ratio. Basically, the ratio of this is the density under the alternative. This is the density under the null. So the ratio of the density under the alternative to the density under the null. And if this likelihood ratio is bigger than tau, so this expression can be written more in a more readable fashion as 1 if L of x is bigger than tau, gamma if L of x is equal to tau, and 0 if L of x is less than tau. Okay, so what this is saying is if L of x is bigger than tau, we say that the alternative is true. If it's less than tau, we say that the null is true. If it's equal to tau, we randomize. If you flip a coin, this gamma is in 0 to 1. And with that probability, you decide whether to declare one or not. So this is going to be the probability of acceptance or rejection of the norm. Right. So remember the delta x means rejecting the norms. The probability of this is the probability of, let's say, accepting h1 given x is equal to x. So that probability accepted. Okay. So that's what Bingham Pearson tells you. So the likelihood ratio comes up again as an important statistical quantity. Yes. Tau is a threshold. So this is something that you have to determine. And the way you determine this is by saturating this inequality. So you're going to choose tau, such that this hits alpha. So then that would be the most powerful test at level. So a formal, I can give you a formal statement here. I'll give you the formal statement. So consider a family of randomized likelihood ratio tests of this form. So the parameters like series P instead of tau. So this used to be tau. You think of it tau. And gamma, which is this parameter. So you have this sequence or family. The idea is that, so this is the same idea. So P1 divided by P naught is the likelihood ratio. And rather than writing it like that, you can write it like this because this is less ambiguous. So there's no division by zero here. So this makes sense even if both sides are zero, or one side is zero. But roughly speaking, you don't worry about division by zero, the equivalent. So this is a likelihood ratio test that thresholds the likelihood ratio at level T. And the lemma says for every level alpha, there is T and gamma that they can choose such that under the null, the expectation of the test is alpha. So this is saying I can achieve every alpha that you give me by properly choosing tau and gamma. And the reason why we actually don't randomize here is for part A here, because if you don't allow me to randomize, there are cases in which I can't necessarily achieve alpha. I could be less than alpha, but to precisely achieve alpha, sometimes I have to randomize. And when do I have to randomize? Just give me a second. So the cases where this happens is where the likelihood ratio, the distribution of the likelihood ratio has a mass, point mass. Maybe we'll talk about that later, but this is true. And once you achieve this, if the family achieves this alpha level, then by part B, it's going to be the most powerful test. So a likelihood ratio test that achieves the level alpha is the most powerful test at level alpha. And any most powerful test at level alpha can be written as a likelihood ratio test that's part C, which we ignore. But basically, there's nothing else. So all the possible solutions are of this form. Is that clear? Yes.
So if we set alpha, like say 0.05, and technically can get a ratio test, that's nice.
Yes, yes. So this is saying for a general problem, it's possible that using properly the T and gamma to achieve this. You achieve this, and then if you set this to be like that, then this would be the most powerful test at level 0.05. Okay, maybe let me give you the heuristic argument. And if you have time, we can go to other part. But the idea, the basic idea is this is an optimization problem, right? And I can it's a constraint optimization problem, and I can use Lagrange multipliers if you remember to turn a constraint optimization problem into a unconstrained problem. So this is the easiest way to solve this. And in order to do that, we basically I'm going to write this as for simplicity, I might write 1 instead of theta 1. You see, instead of this is like, instead of writing theta I, I'm going to write EI. So the problem is supremum, or let's say maximum if you want. Delta overall decision rules basically of expectation under 1 of delta x, that's the power, subject to expectation under null of delta x. Okay, let's do 0 here. And so this is sort of equivalent by Lagrange duality to maximizing, so it's less than alpha, maximizing this E1 delta x plus lambda times, let's say, alpha minus expectation of delta x. I rewrite this like that. Let's say alpha minus expectation of delta x is bigger than or equal to 0. And then this is a constraint. I dualize it in a sense. So the Lagrange multiply theory tells you that for a given alpha, there's going to be some lambda solution of this, same solution of that. Okay, and in order to maximize this, we can focus on maximizing basically this part, delta x minus lambda E naught of delta x. There is the part which we don't need to worry about because it doesn't depend on alpha. So I just have to maximize this part. This doesn't depend on alpha. Okay. And here the idea is that I have expectations under 2 different measures. I can pull them or like put them both in under the same measure to get to pull the 2 terms together. So how do we do that? You want to remember this, the device. There was a device that allowed me to change the measures. No, change of something else. Like I want to change the underlying measure. And then, so I'm integrating this one integrates. This is like delta x p1 of x dx minus lambda integral delta x p naught of x dx. Okay, good. So I write it as basically Lx times P1 of x, or sorry, the other one, right? L of x, P naught of x dx, right? So this is, and then I can combine. So I get delta x, L of x minus lambda delta x, and then integral P naught of x dx. Right. So if you just go back to the discussion of likelihood ratio, this is exactly the result that we had. You can exchange the measures by multiplying. So I'm evaluating this. I can transfer it to under E naught by multiplying by the likelihood ratio. Right. Okay, good. So I want to maximize this. So this would be like that. So this is maximized, if I maximize it pointwise. So this is taking expectation under the distribution of x, but if I can make this be as large as possible, for every particular x, then the expectation would be maximized. And the way to do that, in one case, we have to do that. The delta x takes values in 0 to 1, but the maximum value that can take is 1, the minimum is 0. Right. Any idea? You want to maximize this for any particular x. The delta star x is going to be the one that is gonna be one, whether this is positive. Because then it will contribute positively. Right, if it's positive, I want to maximize as possible, so I'm gonna take the cap, which is one. If it's negative, I want it to be as small as possible, so make it zero. So the solution, if you think about this, would be if this is bigger than lambda, it's going to be one. If this is less than lambda, it's going to be zero. If it's equal to lambda, it doesn't matter. We don't care, at least as far as this goes. So this sort of gives you the structure. Yes.
I have a question, if you scroll up a little bit to the beginning of that, yeah, that equivalence relation that you wrote on the
Yeah.
third line.
Yes.
I guess I was a bit confused by that, there needs to be some like conditions for that to actually be an equivalent problem, no?
Generally, yes, there should be the conditions. But I'm doing a heuristic argument, right? And when it turns out that this, in this case, so because it's a linear program, so if you think of these as integrals, this is a linear function of delta, and this is also linear, so it's like an infinite dimensional linear program. So it would be, it falls within the convex optimization framework, and if you're interested, you can look at Keener's. He provides a like a rigorous sort of proof of this.
Okay.
But it's a linear programming. In fact, you can do a duality. So I think you could do like inf over lambda, and it would be equivalent in a sense, like min, max, min or duality. But this was a heuristic argument. So once you figure this out, you can make it more precise, but just once you figure the structure, I can just prove that this is actually the optimal. That would be easier. So that's what this argument here is doing. And then you don't have to worry about the division. And then you see why the saturate. So I'm going to go over this quickly. You can just do this proof for yourself. This is rather easy. So let's prove part B. So let's start with aggregation that achieves this bound. Then any other rules that I have that satisfy the inequality would satisfy this. Basically, is not level of most alpha satisfies inequality, and alpha by assumption is equal to the level of the likelihood ratio test under consideration, so it's equal to that. Then you would write this inequality. This is rather straightforward rewriting of what we did. So this is saying if P1 is bigger than P naught, this is going to be 1. Okay, so this is going to be positive. This is strictly positive. First, I can rearrange the thing. So for any x for which this is strictly bigger than 1, bigger than 0, this would be 1 by assumption. And I can drop both sides. So this cancels out. This is delta x is less than or equal to 1, which is true. If it's less than 1, sorry, less than 0, then this would be 0. And when I cancel this term, the inequality is flipped, and I get delta x is bigger than or equal to 0, which is true. And if this is equal to 0, then both sides are 0, so this holds. Okay, so this inequality holds. Then I'll take the equation under, or like integrate, basically integrate both sides. If you integrate, you get E1 delta x minus P0 delta x, and E1 delta side x minus P0 delta x. You rearrange, you arrive at this inequality. That's the same thing that we did. So this thing is less than or equal to 0 because of this. If you rearrange that, you'd see that this is less than or equal to 0. So it says that the other side is less than or equal to 0, which says that E delta star x is less than or equal to E delta. So this is a proper proof inspired by that argument. Okay. And here we use the fact that it saturates the alpha for this situation. If it's less than alpha, then I can't say this is really less than zero, but. Sounds good. Just go through this you can verify under the three conditions. And so any likelihood ratio test that saturates that inequality would work. Why can you achieve that inequality? Is there any questions? That this is called the Navier-Pearson lemma, and it's just a the very important classical result. Yeah.
The term saturate. Satisfy.
Saturate, I mean, satisfy with equality.
Saturates.
When I say saturate inequality, so you can satisfy the inequality in strict equality. When I say saturate, it means satisfy this thing becomes equal, the largest they can be. Right, that's fine. Saturating an inequality means that you hit the boundary. Like this. You can satisfy this inequality if you're below alpha or if you equal alpha. Usually when you hit the boundary, you say we saturated this. They can do bigger. Okay. Terminology doesn't matter, so as long as you understand what I'm saying is like you have to push this to hit alpha to get the most power. Intuitively, it's clear. And in the proof also comes up. A very minor point about why you can always achieve this or how you can actually. So the plan, if I ask you, for example, to compute the most powerful test for a given simple hypothesis test is to write this down. And then given the alpha, try to satisfy this. This would give you the solution to T and gamma. So how does that work? In general, you would form this something like the complement of the CDF of the likelihood ratio under P naught, because we want to work under P naught. There's a statement about P naught. So you find the distribution of X under P naught. So this probability is as a function of T, it will have. It's basically the CDF. 1 minus the CDF of the likelihood ratio. Z is the likelihood ratio variable. This is the 1 minus the CDF under the null. And so this would be right continuous and non-increasing. So it starts from usually around, like at infinity, negative infinity would be 1, because the CDF would be 0. And it drops down, in one case, it's like very continuously. So basically continuous distribution. If it's like this, then you're good. Why? Because I can achieve, I want to achieve this. This is doable if I set gamma equal to 0. In that case, the expectation of this would be just, so set gamma equal to 0, then the expectation would be just the probability that this is just L of X. L of X is bigger than T. Okay, which is this function, that G of T. So I really want G of T to set G of T equal to alpha. And so T would be G minus 1 of alpha. Okay, I'll go look at the alpha level that I want maybe here. And then this point would be G minus 1 of alpha. So that would be my threshold. So I can achieve that equality here by setting down there is no randomization needed. And I just invert this. It's like similar to the quantile function, but basically the inverse of this function. Okay, so that's one particular case. But the difficulty would be the case where I have maybe something like that, it comes down, and then there's a jump. Okay, so this corresponds to the case where you have a point mass at a particular location, P naught, for example. Okay, if there's a point mass in the distribution of L of X, you would have this discontinuity, jump discontinuity. So in this case, things are still fine if, for example, your level hits this part, because there is the solution here, and I don't need to randomize, I can do as before. But the tricky part is when like your alpha is such that you hit this intermediate portion, or like this jump. So there is no particular value at which this probability is equal to alpha. So if I take, for example, T naught, the probability would be this. If I slightly below, the probability would be here. There's nothing that exactly equals alpha. Okay. How do I deal with this? So I would randomize, I can interpolate basically everything in between. That's the point of gamma. So in this case, what we want to do is we want to take what do we want to do? We want to
Portion, like we see where that alpha is, to gamma.
right. So first, by viewing this, you realize that the right position for that T would be this T naught. So here I want to have yeah, this is the electric tree. Is this correct? I think I should have probably something like it should be right continuous. Okay, so this wasn't correct. So that's the okay. So this is right continuous. So the right position would be, so the threshold to be, I have to take the threshold to be T naught. So in that case, the expectation of delta T and gamma X would be the probability that L of X is bigger than T, plus gamma times the probability T naught, plus the probability, this would be T naught, that L of X is equal to T naught, plus 0 times the probability that this is 0. Okay. So that would be like this. And this is, for example, what are we going to call it? Let's say this is G T naught. Okay, so this is going to be G T naught. Right? It's fixed because I figure out that once I pass this alpha through this, I know what T naught is, and G is known. So this should be below alpha. Okay. So what I get is this I want to be alpha. This I know, and I know this is less than alpha. So alpha minus G T naught is going to be positive, divided by probability of Lx equal T naught. That would give me gamma, and so this would give me something positive, and also going to be in 0 to 1, bigger than 0 because this is less than alpha, and at most 1 because this sort of difference is this probability exactly equal to T naught. So this is guaranteed to be in between. So that's like the fraction of the mass that they need to. So this is exactly the amount. So the ratio of this to this gap is going to be the amount of randomization thing. Okay. So this is the general like pictorial way of arguing that A is always achievable. So you either hit a location where there are other cases where you can hit the flat portion. There's a flat portion, but then there you still can find a theta naught that achieves the probability. But the tricky part is when it's not possible. Set equal to theta naught, my probability is the level will be less than enough, but if I'm a little bit above, it will be very high. So that's what we do. Okay. Sounds good. Okay, so let's do an example. So we have X is normal, theta 1. There are two hypotheses. Theta 0, theta 1. And I form the likelihood ratio. And the idea is that the test is going to reject. So this, we know, in this case, everything is continuous. So we're not going to run into the issue of that I just discussed. So the test rejects H naught bigger than P, and except H naught less than T. And at E equal to T never happens. Probability like 0 happens, so you don't have to worry about it. And it's up to you to decide what you do, what like you define it arbitrarily. So I set it bigger than t, and then you often manipulate it. So you take, for example, take the log, it's the same. So just take it. It's a little equal. So they set up all x such that L of x is bigger than tau is the critical region of the test. So this is not going to change the log. So the log of L of x is bigger than log of t. You do some manipulation, and in the end, at some point I have to divide by this if I want to simplify further. And I have to be careful because if I divide by something that's negative, it changes the direction. So I'm going to keep the sign. So this means you can write the sign times the absolute value. The dividing by the absolute value, you keep the sign here. And then that's the structure of the test. So if, for example, theta 1 is bigger than theta 2, then this is just 1. So it says x should be bigger than something. And then the advantage is that I'm going to call this tau. And I just have to specify this tau. Like which is going to be a function of t and these guys, I don't have to worry about this t. Because what I need to satisfy, I know that this is going to be like relation. So let's say theta 1 is bigger than theta naught. I know that the test is equivalent to this, x bigger than some threshold. And then I can set this threshold by requiring the power to be updated secondary, the level to be out. So the level of x will be the probability of rejection of the null, in this case that. So I set this equal to alpha and I solve for tau. And in this case, the solution would be so Q function is basically, so under the null, basically, so I can write P naught of x bigger than tau is the probability that theta naught plus a standard normal is bigger than tau. Okay, because we're under this model. This model can be written as x is equal to tau plus z, where z is standard normal. And so this is equivalent to saying that z is bigger than tau minus theta naught. And so this is called the Q function. So Q tau minus theta. So this is the 1 minus the CDF of the normal, standard normal. So we want to set this equal to alpha, then this gives me that tau minus theta naught should be Q minus 1 of alpha. Okay, so it's related to the quantiles of the normal, but you figure out tau, and then you're done. So your test is basically x minus theta naught being bigger than Q minus 1 of alpha. So you really don't need to backtrack and figure out what T is. The test is equivalent to this. And we know that, so this is a likelihood ratio that achieves low alpha, so by the Pearson lemma is most powerful. Okay. So this procedure is very interesting. In particular, if you contemplate this, you realize that theta 1 doesn't matter. Okay, so and you can see like the test is the same no matter what theta 1 is. So this is going to be most powerful against any other theta 1 which is bigger than theta naught. Simultaneously most powerful for all of these hypotheses, no matter what theta 1 is, as long as theta 1 is bigger than. So this is what is known as uniformly most powerful test. So if you understand what happened here, then you realize that we proved that this particular test is uniformly most powerful against a composite hypothesis where we assume that theta belongs to this omega 1, which is like all the theta that are bigger than theta naught. So if we solve this simple hypothesis test, and you realize that this one doesn't matter up to, it doesn't need it to be bigger than theta naught. It can be simultaneously most powerful against, because if it's below theta naught, then the sign changes and then the structure of the most powerful change clear. So I have to reject that x is smaller than. But as long as theta one is bigger than theta naught, the test is equivalent to this and it's independent of theta one. So this particular test is most powerful against every one of the like alternatives in this composite. So it's uniformly most powerful against this composite hypothesis test. That means that it maximizes the power at every point of the alternative, subject to the size of the most powerful. Okay, so these are called uniformly most powerful. We'll talk about hopefully very soon. Okay. Yes.
It's more confusing about the difference between the most powerful test and, let's say, hypothesis testing. Because isn't, if we have a theta one closer to theta naught, we could have like failed to reject. But if theta one is very far, like that would make a difference in the hypothesis testing.
So hypothesis testing is the problem. I set up the problem. So I give you theta naught and theta one, right? Whether they're close or not at all, fix. Okay. Then you can ask, what is the most powerful test? Right, right. So let me show you this. So we can calculate the power of this test. Like let's say fix theta one. You guess a particular alternative. So x minus theta one is normal 0, 1 under q1. And so the power of this test would be the probability under 1 that x is bigger than tau. That's by definition of the power, which is the probability, again, I'm just subtracting theta 1. And x minus theta 1 is some z here. So this is equivalent to probability that some random variable z normal is bigger than tau minus theta 1. And I'm going to apply, so this is the key function applied to tau minus theta 1. And I can replace this tau with this value, and I get the data power is like this. So if you plug this in here, theta naught plus q1 alpha, this is going to be, I define delta to be theta 1 minus theta naught. And then you can see that this. So we have calculated a relation between beta and alpha for this most powerful test. And I can plot this. So I can plot beta versus alpha. This is called the ROC here. So alpha, well, false positive rate, sometimes called false positive rate, or type 1 error, or significance level. And beta is true positive rate, or the probability of power here. Okay. True positive rate and false positive rate is mostly from classification or multiple hypothesis testing, but power versus significance level. So that's that curve. So Q of minus delta plus Q1 minus 1 of alpha. So this is this curve. So this is beta, this is alpha. Alpha, beta. So this is the trivial test. So this is the test that always accepted probability alpha. It's a randomized test. And you should always be able to do better. And this is the power of the most powerful test. What this is saying is that for any given alpha level, that's the maximum power that's achievable. You can't achieve anything above that. Okay, so if you have a different test, maybe you do something else. So for this hypothesis testing, this is not the only possible test. I can, for example, I don't know, say sine of x is bigger than 1, I'm going to reject. Otherwise, I'm going to accept. Okay. So that would have a certain ROC here. And the ROC here for that would be necessarily below this. So that's the meaning of most powerful. So that would be something like that. Okay. So the thing that you mentioned, whether theta 1 being close to theta naught, so theta 1 gets close to theta naught, the problem, hypothesis problem becomes harder. So this delta becomes smaller, this delta. And this would become like this. So the most powerful test would be this, which means that nothing above this can be achieved. The problem would be harder. If delta is much bigger, then this would become like this. Then the problem becomes easier. So by looking at the ROC curve of the most powerful test, you can see that the problem, how hard the problem is. Okay, this is the maximum achievable. Okay, it characterizes the hardness of the problem implicitly. Does that make sense? Okay. Questions? So you now know the ROC. The ROC is one way of measuring the performance of ROC curve. Both a hypothesis test, like hypothesis tester or like test, and also like classification problem. Mostly for hypothesis testing, though. Originally designed for hypothesis testing, but there's a relation between hypothesis and classification. Okay, and this idea of UMP is what I want to talk next about. So if you have a hypothesis omega naught versus omega 1, for example, let's say I have a coin, I want to test whether it's fair or not. So one could be simple, omega naught could be simple. The other one is like everything else except one. So a UMP test is test of side alpha is called uniformly powerful for UMP of level alpha. If for every other test of level alpha, level is at most alpha, like this is a candidate test. It turns out that the power of delta is bigger than the power of phi for every case having delta. Okay, so this is uniformly most powerful. Uniformly is over like pointwise over every theta in the alternative, while as they vary the phi over all possible tests of level alpha. Okay, so this is like UMVU that we had. So among all unbiased estimators, what is which one has the least variance? This is saying among all tests of level alpha, who has the most power uniformly over the entire parameter space or region of interest of parameter space, which is omega. So we saw that like basically this procedure shows that this test is uniformly powerful for theta naught against which a composite test. That's what this one, theta bigger than theta naught. Similarly, if you argue if theta 1 is less than theta naught, I have like this. So the test is the more powerful test would be x less than tau, then you can argue exactly similarly that there's a UMP test for testing theta naught against the alternative test theta less than theta naught. So these are called one-sided tests. So theta naught versus anything above, or theta naught versus anything below. So one-sided UMP tests exist in this case. But the question, for example, is there a like two-sided UMP test? If we have a two-sided, can we have a test which is uniformly most powerful against this hypothesis? Sorry? Can I have, this is my two-sided, anything but theta naught. And I find a test which is uniformly most powerful against this. So this same argument gives you the answer. What is the answer? Is the question clear? Can we have a test which is simultaneously most powerful for every point in the alternative, subject to the size being equals alpha? So we did the thing, right?
If you do it again with like partition group of space.
So the way that we did, let's say the way that we found out that there is a UMP test for this problem is if you take the particular theta 1, let's say this, and then the calculation up until the end, and realize the test does not depend on the particular theta one that we chose. The same goes for eta less than this. Okay, so, yeah,
Maybe I should say no, because we don't know the sign. So we can't really.
right, so that's the correct answer. So the answer is no, but the exact argument says that if I pick like the theta one here, which is bigger than theta naught, the most powerful test would be this, like bigger than tau. If I pick a theta one, which is less than tau naught, the most powerful test would be a test that rejects when things are less than tau. So the structure of the test changes. There are two different tests that are most powerful for different parts of the parameter space. So I can't simultaneously, so they can't be reconciled. So I can't have a test which is rejecting both less than a threshold and above a threshold at the same time. Right, so this contains everything up to negative infinity. So this suggests that, or it proves actually that there is no uniform most powerful test for this. Okay, so you can prove that there does not exist, there is no uniform most powerful, but calculating the most powerful test for each point. And if it's like true that all of them like coincide, I can combine them together, basically by choosing, in this case, a threshold that does not depend on anything like theta, theta one, then you're good. Otherwise, you often prove that there is no such test. Okay, and so uniform most powerful tests are not necessarily, do not always exist. Does that make sense? Okay, so this is another example with binomials. It does the same, has the same flavor. So testing with respect to a binomial is tau. I'm going to test the theta is 1/2 or not. So you take generic theta one, and then you go over the analysis and you realize if theta one is less than 1/2, there is this structure for the optimal test. And if theta one is bigger than 1/2, the most powerful test is like that, exactly similar to what we did. And so there's no UMP, two-sided UMP test because the structure changes. So this statement or this argument that we did can be generalized. And the reason why it works is because so that the likelihood ratio is monotone in X. So whenever theta one is bigger than theta naught, L of X being bigger than tau is equivalent to X being bigger than something else, or X this being bigger than T is equivalent to bigger than tau. This property is called the monotone likelihood ratio property. So this result is basically generalizing that argument that we did. So a family of densities has monotone likelihood ratio in a certain statistic, T of X. In our case, it was just X. If whenever theta naught is less than theta one, then the likelihood ratio is, for example, non-decreasing function of T of X. So this likelihood ratio depends on theta one. If theta naught is less than theta one, I want the likelihood ratio to be non-decreasing. Or you can say not increasing. It should be monotone either way, because I can change T of X to negative T of X. And it would be fine. So let's say non-decreasing. It doesn't matter initially. It just has to be monotone. It doesn't go up and down. So if that's the case, then there exists one-sided UMP test. And can be written in terms of this TRX. So this TRX does not depend on the theta. For example, if you have an exponential family, 1D exponential family, you can form this likelihood ratio. If theta is monotone, right? Whenever theta one is less than theta, let's say theta one, then theta naught is equal to theta one. And so we have this is positive. And this whole thing is exponential, something positive times T of X minus the cost of constant. So this is monotone increasing in T of X. So the likelihood ratio would be the monotonic function of T of X. So we have the monotone likelihood ratio property. Similarly, if it's like decreasing, the area is decreasing, this would be negative, so this would be monotone likelihood, have monotone likelihood property minus T of X. So either case, if it's eta is either increasing or decreasing, it has the property, and in that case, this would, so this includes some of these like Bernoulli, binomial, Gaussian, Poisson. So in this case, we have this result, which is proved exactly like we did, that theta family has a monocolor test in T of X. And if you look at these one-sided tests, and in particular in this case, you can also let theta be less than theta naught. We did it for this, but this result also suggests that I can make the alternative also non-confident. And let's say in this case, consider this case for now, for simplicity. Then this test that rejects when this T of X is bigger than C is going to be UMP of psi alpha. And then you have to also normalize to be able to achieve the power, the power of the test. But the power is sort of, this is the power function. This is like expectation basically of delta X. So this randomization is understood there so that we can achieve this. But roughly speaking, this test doesn't depend on which theta 1 or theta, like which theta you're taking, because TRX is just a statistic, and we know that the likelihood ratio is monotonically this. So this argument that exactly the argument that we did suggest that this test, the final test with UMP, and I have to say C such that it's equal to alpha. Then by name of Pearson, basically, this is going to be simultaneously most powerful for every for every basically theta here versus theta there. Okay, so I'll let you like prove this for yourself. At least this part should be very clear. So you just start down writing the likelihood ratio, like you name a Pearson sort of argument. By name of Pearson, we know that the likelihood ratio, the optimal test is something like that. And then you manipulate this inequality and write it in terms of TRX here, which is doable. And the part about this being non-common, I'll let you think about that yourself. Sounds good. Okay, so UMP tests are generally hard to achieve, but sometimes, like this case, they're one-sided UMP tests. The next step, which we don't go over, is like, okay, maybe if I restrict the class of functions or class of tests, then there might be UMP tests within that class. And then they had the notion of unbiased tests, which is different than unbiasedness of estimators, but you can look for uniformly most powerful unbiased tests. And oftentimes there are those things. And for that, you should check out the book by Lehman, Classical Hypothesis Testing book by Lehman. Okay, so the last thing so any questions so far? So you have the name of Pearson, you know, like what is the most powerful test for simple hypothesis testing, and sometimes that can be generalized to UMPs because the structure of the test doesn't change. And in one particular case, you have one of the likelihood ratios and one-sided test basically. So the last thing is, okay, I'm in a situation where I don't have a UMP, I have this two-sided problem. Maybe I don't care about like being uniformly most powerful. Can you suggest a good test? I mean, I have to do a test. And so this idea of generalized likelihood ratio test is very useful because it gives you a general recipe. You don't have to worry too much about whether UMPs exist or whether even if they don't exist, this is going to do something good. So the idea is that I have a composite hypothesis. And this is a form of the likelihood ratio between two different parameters. I don't have a specific parameter. I'm going to look at the maximum P theta X divided by the maximum P theta X over omega naught. So this maximizes the likelihood over the entire parameter space. This maximizes over the norm. So the ratio of the maximum likelihood or the maximum likelihood over the omega naught. In particular, if theta hat is the unrestricted maximum likelihood estimator, this is just should be theta hat x. And this would be p theta hat not of x, or p theta hat not is the maximizer of the likelihood over this part of the parameter space. So this statistic is called generalized likelihood ratio, this for obvious reasons. And it's going to be always in 1 to infinity, because it's supreme over the entire parameter space. So he says it is the supreme over the restricted part. So we reject when this is large. So the idea is that under the norm is going to be very close to 1. Under the alternative is going to be very big. And so we reject for some value lambda. So you reject when L of x is bigger than lambda. Alternatively, you can look at this quantity, which is in 1-to-1, like monotone transformation of L of x. Let's call it lambda of n of x. So we reject when this is bigger than tau, and potentially we randomize if we need to achieve a certain level out. So in the setting of the threshold and this randomization is exactly the same as before. And the reason why you do this transformation is because this thing has a good asymptotic distribution, which I'm not sure if we get to talk about, but I'm going to point this out at the end. So why this is a good idea? Because like roughly speaking, assume that there's no randomization. So we're going to reject when L of x is bigger than some threshold. So when we are under the null, the true parameter is in omega naught. And so when I maximize all the entire parameter space, and when sample size goes to infinity, theta hat is going to approach theta. Theta hat naught is also going to approach theta, because theta is in the region where I maximize. So I can just basically ignore. So this is omega naught, this is omega 1. Theta is here. So when I maximize over this is like a valid maximum likelihood problem. I just ignore this. I'm doing maximum likelihood for this part and the parameters in this model by consistency on the mean. Theta hat is converge to this. The theta hat is always going to converge to this because we always know that theta is either here or here, but it's going to be inside the entire omega, and you're maximizing likelihood over the entire omega. So they approach both approach theta. So these two approach each other, and so you approach 1. Under the alternative, theta would be here. Not here. So theta hat naught is restricted to be in this part of the space. So it's going to never be able to like approach theta. It's going to try to approach this, but it's going to hit the boundary. So you end up like this is going to converge to a projection of theta on the boundary. But in any case, it's going to be different than the actual. So theta hat naught is going to tries to approach theta, but can't really get to it. But theta hat is going to easily approach theta. So you get two very different solutions here. So this is going to be much different than this, and so the value would be higher, much higher. Sounds good. Okay, so like one example is when you have normal distribution, mean and variances are unknown. Let's say I have one parameter which is standard normal. So mean is 0, variance is 1. The alternative is anything but this. So I want to test whether my sample is coming from a normal distribution, standard normal, or not a standard normal. So you maximize the so under the alternative, so under the norm, there's just one parameter. So this maximization under the norm is just simple. It's just you write the density of the standard norm. There's no maximization rate. And then the nullness. And the alternative, you maximize it with your usual maximum likelihood estimator under the normal, and then you plug in and get the expression. And then you divide, you simplify, and that likelihood ratio, we rejected this to get a certain threshold, and we want to set the threshold by making this be equal to alpha. Alternatively, we can set the threshold by taking the twice the log of this and comparing that to a threshold. And that would be twice the log of the likelihood ratio, and this is a reasonable quantity. Okay, well, after simplification, basically, we're looking at this quantity. The issue is that figuring out the distribution is under the norm might be tricky. Okay, so in order for me to set this, I want to set this to be equal to some threshold. So I basically want to say, or I can absorb the n into the threshold as well. So I want to say, okay, I really don't want to absorb that, but I want to say, what is the probability that this is bigger than tau? And then I want to set it equal to alpha, figuring out the distribution of this quantity for that quantity star. For that reason, people have developed the time theory that tells you under the null this is going to converge in this distribution. This quantity is going to converge to a chi-squared with r degrees of freedom. And r is the difference in the dimensions of the full versus the parameter space. So in this case, the parameter space is dimension is 0 because it's just a point. And the full parameter space is 2-dimensional. So the difference is 2 minus 0. So this is going to converge to chi-squared. So you can use that fact that under the null, this is going to converge to chi-squared with 2 degrees of freedom to set the alpha. The tau, yes.
Is that this specific case? Since the null is.
No. So this is very general. So this is the statement that I have, which is not even general. So even if the parameter space is curved, under very general conditions, similar conditions that for asymptotic normality that this is an application of those asymptotic techniques that we developed. So this is one example. Suppose that omega is a subset of R. B open, R is less than B. Let's say the null is something like that. So what it does is, let's say if I have a 3-dimensional, for example, space, let's say R is equal to 2. This is saying theta 1 is equal to 0, theta 2 is equal to 0, and theta 3 is only allowed to vary. So that's my null would be, for example, this. Okay, the entire parameter space is 3-dimensional, the null is 1-dimensional. And so the difference would be 2. Or in general, it would be R constraints. So the dimension of the null would be v minus R. So that's the dimension of the null because I have R constraints. Dimension of omega naught would be v minus R. And then the dimension of the full parameter space is V. And so this is going to converge under the regularity assumptions for the MLEs that we had to a chi-squared with V minus R. Okay, so that's the answer to your question. And this is actually the local dimension. It doesn't have to be these parameters. It just has to look like this. Where does it have to look like? Locally, it has to look like this. I'll let you look at the key there. It's like a very later chapter. But let's say for this case, you can actually prove this. But in general, there's like a manifold, and locally, it looks like in equal space. Like this is the local behavior of the space, like the null versus alternate. But let me maybe point out what the proof of this would look like, and that will be the end of this lecture and the course. So the idea is very similar to the things that we had done before. So if you take L of theta to be likelihood, and then would be, if you recall, it's just the summation of these. And then if you look at the likelihood ratio, it's not hard to see that you can write it. That was the log of the two. So it's you evaluating it at theta hat n, you're evaluating theta hat not n. This is like restricted MLE is MLE. And so that would be the expression that you have for the gamma, the lambda n. And then, as usual, in these arguments, you do a Taylor expansion. So we're going to do a Taylor expansion around unrestricted MLE. So I'm gonna expand basically m and theta around. So this would be mn theta hat n plus mn dot theta hat n transpose times theta minus theta hat n plus the second order term theta hat, or this is really theta minus theta hat transpose the second derivative, which is the Hessian, at a middle point. This is the same thing as that, and I'm evaluating it at theta being theta hat naught. So I'm expanding this and evaluating it at theta hat naught. So the value of theta hat naught is approximately the value at theta hat n plus these terms. Okay, this is Taylor expansion around. So this with theta equal theta hat 0 n. Now that's the second order Taylor expansion. And then we know that this quantity is going to be 0 because the MLE is maximizing this. So that's going to be 0. And so we end up with this quadratic term. And so this, by the similar arguments that we had, like you remember this stochastic equicontinuity, this is going to converge to the negative Fisher information plus OP of 1. And so in the end, I can rewrite this as so negative twice. So this is basically negative twice n times that. So if I multiply by negative, so this thing is going to be multiplied by negative 2n. So you get rid of the 1/2, you get the root n's here, and so you get in the end this expression plus OP of 1. Okay, and if I define an inner product like this, Z transpose QZ, this is an inner product, and so it's a particular node. And in this notation, I can rewrite it as basically we're measuring this difference in this norm plus OP. And finally, we note that the maximum likelihood estimated has this MLE, sorry, the asymptotic normality, if you remember. So this is like that. Let's say for the, under the alternative, we just had one, I'm just doing it in this case for an alternative which is simple. So let's say just sorry, but no, it's simple, take it on. So in that case, this is just going to be, if this is simple, this is just going to be theta naught. Okay, so there's no maximum likelihood under the null. So this really is going to be convergent. This is like the normality in the mean. And so if I look at this, I can write it as this matrix times Z, where Z is a normal random variable, and then you evaluate. So this is basically to replace this here into this, and then you evaluate this, and turns out to be just the norm of the square. So what I'm saying, like what we proved, is this is converging to the norm of a normal random vector, and this is chi-squared. Okay. In this case, we need to use a proof because the norm was like that. So the proof is up to this point is general. At this point, I just assume that basically R is equal to D. So let's say all of these are equal to 0. And so this gives you a simple proof. In a more general case, you can try to argue similarly. Okay, we're out of time. Any questions? So this was a little bit fast, sorry. But you should be able to follow if you go through. The main idea is that you do the expansion. The first order term managed, the second order is quadratic. And this is sort of convergent to a normal. So you have a quadratic of a normal. And the idea is sort of interesting. This expansion is interesting. It says that this like equation, measuring some sort of a distance between these two elements with particular metric, which is defined by the Fisher information. So it has a lot of statistical equation, which unfortunately we can't go into, but it's a very nice proof to go through as like an exercise for yourself. Questions, comments? So that's a good place to stop. Thank you guys for a great quarter, and it was a pleasure teaching you. If you have any questions, let me know. We can like be in contact while you're at the side, but otherwise, good luck on your final exam and see you around.